Okay, so this video is going to cover problem set 1, which deals with resonance. So let's look at question 1. Fill in the curved arrows that convert the resonance structure on the left to the resonance structure on the right. So you should have arrows on the first and second structure as your answer. So when we first are given this question, what we want to do is work around the charges. So in this case, we have a positive charge here. And the first thing I would think of is looking at next to the positive charges, you have this double bond right here, and these two electrons can door hinge and swing over and form a bond here. And if you look at the next structure over, that's exactly what we have. The double bond forms between the second and the third carbon, and then the positive charge will go on to the fourth carbon from the left where there is a deficiency. So now we're given the second structure, and same thing, look at the charge, and let's work around that. We could swing this electron back, but that will just bring us back to the first structure. That doesn't really make sense. So the next place to go is to look at this nitrogen, and it has lone pair of electrons, and then those can swing over. And once that swings over, we're given this final structure. And this structure we know is the correct answer because the electrons from the nitrogen swing over, forming a double bond, and with all resonance structures, the charge must remain the same across the whole molecule. Okay, so this one is done. Okay, now let's look at question 2. Fill in the curved arrows that convert the resonance structure on the left into new resonance structure contributors. So in this case, we don't have any new structures, so we have to kind of make our own structures. So same thing, first step is locate the charge, and we're going to work around that. So in this case, this carbon has a negative charge, and if we take these pair of electrons right here and swing them over like we did in the last question, that doesn't really make sense because the charge is negative, and then the carbon would have more than its orbitals can fill. So in this case, the electrons are going to move from the rich area over. They're going to door hinge over, and we could draw a structure like this. All right, and now let's check ourselves. This, in this case, would not be a good resonance structure for two main reasons. First of all, we lose the negative charge, which needs to be constant throughout all resonance structures, and the even bigger red flag is that this carbon right here, the third carbon from the left, has 5 bonds. So that is a big no-no. Let's get rid of that. And then that, sorry. We're going to get rid of these pair of electrons, and then back on our first structure, the double bond electrons have to go somewhere, or else this carbon's going to have too many bonds. So then these ones will swing over and go into this carbon. And then everything is good. Our charge is the same, and we don't have any carbons with more than 4 bonds. And the same thing would occur for the next set of resonance structures, but just over a couple atoms. So we have this pair of electrons, swings over, forms a double bond, and the double bond that originated will go onto the carbon. So our final structure should look something like this. With the negative charge on the last carbon. Alright, so now we're done with question 2. So now let's move on to question 3. Draw the one best resonance structure for the species below, including non-zero formal charges. Circle the resonance structure that contributes more to the hybrid. So in this case, there are no charges to work with initially, so it might be kind of tricky, but know that whenever we have a double bonded oxygen, like this one here, this can swing up onto the oxygen here. And if something leaves, we don't want that carbon to only have 3 bonds, so the nitrogen double bond, or sorry, the nitrogen lone pair is going to swing down at the same time. So we're going to have something that looks like this. I'm going to highlight the electrons that moved, and remember to keep the charges the same. Over here, this is going to be a double bond, and this one is going to keep a positive charge. So now this is the best resonance structure, and we can double check with this has a net charge of 0. This also has a net charge of 0, with the +1 and -1 canceling each other out. And if we were asked to circle the best resonance structure, it would be the first one, because a resonance structure without any charges is always going to be more stable than ones that do have charges. Okay, now let's move on to question 4. Draw the 2 best resonance structures for the species below. Okay, so we're first given a charge. That's a good place to start with. And we have this pair of electrons that can swing on to here. That's the first thing that jumps out to me. Okay, so we have something that'll look like this. And with all resonance structures, the positive charge needs to remain in the molecule somewhere, so it's going to end up right here. And then it's asking for the 2 best resonance structures, so we can have one more resonance structure. And remember that the resonance arrow looks something like this. On your homeworks, we saw some resonance arrows that didn't look like the resonance arrows, and you just want to be as clear as possible to get as many points as possible. You don't want to lose points on this kind of silly stuff. Okay, so with this next set of resonance structures, we have the same kind of principle. Electrons up here can door hinge down here where there is a deficiency, and thus form a resonance structure that looks like this. And the positive charge has to go somewhere. It's going to go on this carbon here. Okay, so the question then asks, circle the resonance structure that contributes more to the hybrid. So in this case, they all have the same amount of charges. They all have a positive charge. They all have the same amount of bonds. So we're going to look at the positive charge throughout the molecule. In this one, this carbon right here is attached to how many carbons? We have 1 carbon here, 1 carbon here, which makes this a tertiary carbocation. Same thing with this structure here. This one is attached to 1 carbon here, 1 carbon here. I'll draw arrows to indicate the attachments. Okay, and this is going to be a secondary carbocation. And for this carbocation, let's see how many carbons it's attached to. We have 1 carbon up here, 1 carbon down here, and another carbon over here. So this is a tertiary carbocation. And the tertiary carbocation is going to be the most stable. And therefore, it's going to contribute the most to the resonance structure. Okay, lastly, question number 5. Draw the 3 best resonance structures for the nitrate ion, NO3-, and circle the resonance structure that contributes the most to the hybrid. If multiple contribute equally, circle all, yada, yada, yada. So in this case, we want to first figure out what the structure of the nitrate ion looks like. And I would say that first step is to count the number of valence electrons here. So we have 1 nitrogen, which is in the 15th group, which means it has 5 valence electrons. And then we have oxygen. There are 3 oxygens, so there's going to be 3 times 16th group, means it has 6 valence electrons. So this is going to be 5, and this is going to be 18. And then there is a negative charge as indicated here, so that we can just add another electron as well. Another 1 electrons, and this total is going to give us 24 electrons. Okay, so in this case, we can draw out our structure, and it's going to look something like this. The oxygens over here. Okay, and this was an answer in some of the questions that we've gotten, and this is actually not one of the best contributing resonance structures because of all the all the charges up here, and this nitrogen is going to have a +2 charge, which is very unfavorable. So instead, nitrogen is going to, or sorry, the resonance structure is going to look something like this, with one of the oxygens forming a double bond. And a positive charge here. So this is going to have an overall net charge of -1. You can double check that. 2 negatives and a positive. It's going to be -1, which is consistent with the nitrate ion as indicated up here. Okay, and we're going to draw 2 resonance structures. So the best 2 resonance structures are actually going to look identical to this one, but just different oxygen atoms contributing. So in this case, when we have a double bonded oxygen, the electrons can swing up like this, and one of the other electrons must swing down. So then we have a resonance structure that looks like this, something like that, with a negative charge here, a negative charge here. Nitrogen has a positive charge, and this is going to be what our resonance structure looks like. I'll highlight the atoms that move during the resonance. And there's also one more resonance structure. I'll draw this up here. I'm running out of space. But it's going to pretty much be the exact same thing, but with different atoms moving. So in this case, we can have these electrons swing down, and these electrons swing up, which will give us a resonance structure that looks like this. Positive charge on the nitrogen, negative charge right here. So if you guys notice, all of these resonance structures look pretty much identical, and these are the best resonance structures, and because they are identical, all 3 of them contribute equally to the resonance structure.